My name is Ted Lederis, so I'm an assistant professor in DMICE, and I'd just like to introduce Sean Babcock. And I wasn't told that I was supposed to make this introduction, so it's going to be mercifully short. So Sean is basically going to present computer-aided diagnosis of prostate cancer using multi-parametric MRI, evaluation of feature extraction and classification. Take it away, Sean.
Thank you. Okay. I know something on this one. We changed the name, now it's a computational biomedicine. For those who want to know. Okay. Grab since my speaker's notes won't show on my computer. Okay, so I'd like to do a little introduction and background on the prostate cancer and the methods of diagnosis. So prostate cancer in the United States. So the NIH 2018 projections for the prostate cancer will be the third highest in new cases reported in 2018, and that's behind lung cancer and breast cancer. So you can see we've got about 10%. Prostate cancer accounts for 10% of the new cases. The top three that I've listed actually account for 50% of all the new cases. So lung and breast cancer are much higher than prostate cancer. And so the prostate cancer 5-year survival is quite high at 98.2%. However, there are keys to that survival rate. And the first is tumor size, so early detection. We can catch the tumor when it's small and have a better chance of treating it. The next is localized and regional confinement. Localized confinement is to the prostate gland itself. The regional confinement is the prostate gland itself and lymph nodes around the prostate gland. Anywhere else it's metastasized, the 98.2 drops dramatically down into the 30% range. And then the third is we have to have accurate assessment of the aggressiveness of the cancer. And the aggressiveness of the cancer is measured by a Gleason score. The Gleason score is basically taken from biopsies where we look at the cells and compare the amount of cells that are normal cells, normal healthy cells, non-cancerous cells, and cancerous cells. And the Gleason score is made from those ratios. And the Gleason score, the way it's generally concept of the Gleason score is if it's 7 and above, it's on a range of 1 to 10. If it's 7 and above, it's considered clinically significant or aggressive, and then that leads to treatment. If it's below a Gleason score of 7, then it's usually just monitored over time to make sure that it doesn't get any worse. Okay, so current prostate cancer diagnosis methods. First is the prostate cancer screening using one of two methods, either a prostate-specific antigen blood test or a digital rectal exam. Now, given that we have an elevated PSA or DRE abnormalities are found, the typical is to go to biopsy, which is either a blind biopsy or a transrectal ultrasound guided biopsy, which is image guided. Blind biopsy uses actually an array of 12 small needles, and it's just what it says. It's blind, they go in and hope that they find the area that would be causing the abnormalities or elevated PSA level. The trust-guided biopsy goes in with just the one needle because it's image-guided, and we'll take samples of the cells, and then from there, we can calculate the Gleason score and determine next steps of. Now, down the other line in biopsy is magnetic resonance imaging MRI-guided in bore biopsy. Very large word. And that's basically using instead, it's image-guided obviously, but instead of the trust biopsy, we use the MRI machine. Now this, obviously using the MRI machine is more expensive, and some facilities may not have access to the MRI machine, so they would default to this. Also to note that if we do get an elevated PSA level, and one of these two biopsy methods comes back negative on the follow-up, if PSA level is still elevated, it's recommended to go right to the more accurate in-bore guided biopsy. Okay, so let's talk about the screening methods and the blind and trust biopsy methods and some of the limitations. The prostate-specific antigen blood test has been shown to be quite variable. Even among two patients that have the same cancer level, we can get different levels, and on repeated visits, the levels may vary, and so it is not as accurate as one would like. The digital rectal exam basically looks at the anterior of the prostate gland, which is the peripheral zone, but it cannot detect anything in the central zone or the transitional zone in between, and actually I have a laser pointer, so I don't have to do that. In these two areas, it's not good at detecting that. And then biopsy method. As I mentioned, blind biopsy is just, one would hope that they hit the right area because it's not image guided, and so it may miss the biopsy. Or it might miss the tumor site, which gives more healthy cells than cancer cells, and they will go down. Yes?
Why would you ever do a blind biopsy? Why wouldn't you just do an ultrasound guided biopsy?
I put the blind biopsy in because websites of literature still bring it up, but it's being phased out in place of the trust biopsy. So in place of an image-guided biopsy.
Right.
But the image-guided, the trust biopsy is not as accurate as what we saw going down on the red angle, which was the MRI biopsy.
I just wanted to add, the PSA, even the name say prostate specific, and the tumor actually is not really specific, is a tumor marker. Right now in pathology, we try to really not use that much because it can be elevated in multiple situations, several like inflammation or obstruction. So it's not really a great tumor marker.
Okay. Very good
That's
information.
why it's really
I will add that into the pilot. Okay, so let's get to the more accurate of the image-guided biopsy, so which is the in-bore guided biopsy. And so here a human observer, usually a radiologist, will examine the MRI images looking for regions of interest, so suspect regions. And then those regions of interest, they will determine did they look malignant, did they look benign. And the malignant areas will be targets for a biopsy. This is, as I mentioned, improved accuracy, obviously over the blind biopsy and also the trust biopsy method. And this also provides ground truth for computer image analysis, which we're talking about here, because we're getting ground truth from the biopsy to tell us either a Gleason score or simply malignant or benign. However, we still see the possibility of over-biopsy just due to human visual limitations. So what is the resolution that a human can look at an image and try to differentiate between a texture that is malignant or a texture that's benign? Obviously, a human can't go down and see every pixel relationship. Also, just the sheer amount of images in a day that someone might have to look at, fatigue, the level sets in, and also the experience level of the particular radiologist that's looking at these images. Obviously, the more experience you have, the better you're going to be at differentiating. And that kind of ties in with, there's generally no set standard for what is malignant looking image and what is benign looking image. And so that kind of ties back into the experience level of the radiologist. Okay, so let's look at the computer analysis of the multi-parametric MRI. So this is a literature review of what's currently being researched and done that I've come up with. And these have basically two goals. So what is the classification of the prostate cancer, either malignant or benign? And then some are will actually try to go in and determine a Gleason score, determine the number of the Gleason score off of the image ROIs. The second goal is accurate targeting of biopsy sites. So that's better differentiation of what is malignant and what should you go and look at to reduce over biopsy of areas that aren't, that are benign and should have been biopsied in the first place. And several approaches are used. The first is a feature extraction and classification, which as we saw on the first slide is the area I'm going to look at. The second image analysis part is deep learning using convolutional neural nets. And then some studies will go in and actually try to use computer annotation of the region of interest. So the computer will go in and segment the image and try to point out what is a region of interest, then analyze is it malignant or benign. Very few do this. Most of the papers that you will read actually use radiologist annotated regions of interest and then start from there. Okay, so what is multi-parametric MRI? So this consists of 4 modalities of MRI images, and I've listed them from the most used to the least used in the context of prostate cancer detection. The first is T2 weighted image, and this relies on the water content of tissues. So it's very good at detecting spatial differences in tissues with different water contents. One of its problems is that it's not very good at detecting tumors in the central zone and transitional zone, which we saw the yellow and green on the other, because the water content of healthy tissue in those zones mimics what a tumor would look like. The second used is a diffusion weighted image, and that looks at the diffusion of water molecules in the tissue. And so that's specifically good at looking at cell types and cell density. So if you take a sample of the tissue in that area, if the cell densities are large and the cell membranes are compromised by being cancerous, they will have less diffusion than with healthy tissue. And from these, the apparent diffusion coefficient map is created from the MRI software, imaging software. And it's the ADC maps that are used in the image analysis. And these will show a darker spot for the darker the area, the less diffusion is shown. And that's how you can tell from there. Next down the line is the dynamic contrast enhancement image. This is much like the diffusion weighted image, but it uses a contrast. It's injected. That's a little more expensive because you have to use the contrast and another round of imaging. So that they aren't used as much in the prostate cancer image analysis. And the least used is MR spectroscopic images. I've only seen them mentioned in one paper out of all the papers I've written. And so that's the least used. So basically, the T2 weighted and the ADC map are predominantly used, and that's what I will be using as the 2 image modalities in this study. And here's just a picture of basically the T2 weighted on the right-hand or the left-hand side, image A, and the RY is indicated by the red arrow. And as you can see, it's very hard, at least for me, to differentiate the region of interest area from the rest of the prostate gland. On this, on the right side, image B, is the ADC map, and you can actually tell that a little more where you can get a little darker area. Dr. Fergus Coakley, that we got the information from the data from, actually said these are nice as going back to project where the region of interest is on the T2 weighted images. And these are from a malignant patient as well.
Is this the same patient?
Yep. Same patient, just the 2 image modalities. Yeah, same patient, both image modalities. And like I said, this was a malignant case. Okay, so the project definition. A long project definition. So we're going to attempt to evaluate the feasibility of machine learning methods, which are feature extraction and classification, for differentiating the malignant and benign tumors for classification with multi-parametric MRI, with the intent of building an algorithm that best reduces over biopsy, and if we really get accurate, enabling in silico biopsy. So if we were quite accurate, we could skip the manual biopsy process and say this is The computer has done the biopsy, and we move from treatment. The model will analyze regions of interest from two-dimensional multi-parametric images. Okay, tools and methods. So, the images we have. So currently we have processed images from 81 patients collected here at OHSU. And those 81 patients break down into 58 malignant and 23 benign. And then from these, we can get 175 malignant and 65 benign images. So what we're saying is we're getting multiple images per patient because the way the MRI will go in and slice, it will take slices, not physical slices, but image slices of the prostate gland for both modalities of the image. So we get more images, multiple images per patient. The regions of interest have been outlined by a radiologist, so we're not going to attempt to segment these. We're using what was outlined by the radiologist. And the MRI inboard guided biopsy was used to provide the ground truth. So that's telling us that we verified that these are malignant or benign for our classification. The good news is more patients have been screened, and right now their image data is currently being processed. So we hope to get this data set larger in the near future.
Do you have a different number of images per participant?
I have a spreadsheet for that, yes. It varies per person. So you get some patients, we have, for instance, 7 T2 weighted images, and other patients may have 3 T2 weighted images. So
The relative size, that sort of thing.
Mm-hmm. And here's just an example of a table here with the, from a benign patient for both modalities, a malignant patient for both modalities, and again, pointing out where the regions of interest are. You can see that the ADCmap show them a lot better than at least what I can see on the T2 weighted. Because this is a projector, it looks a little better on a computer. And then here's just the same image. I hope you can see the red outlines are actually, those are the regions of interest outlined by the radiologist. That's four of those. You'll notice they don't match. Some don't match up directly. That's because when they take the MRI images and they slice for the T2 weighted images and then slice for the diffusion weighted images, they will be a bit off on the registration.
Yeah. I mean, it looks like, well, we should talk afterwards. It looks like there's a number of issues with this case.
Okay, so here's really the heart of the matter for the algorithm flowchart that I'm going to do. Again, starting with the T2 weighted and the ADC, we're going to use just the ROIs and do texture feature extraction from those regions of interest. And that will create an entire texture feature vector. And we'll talk about the 3 methods that we're going to use on the next slides. And from this, we will do a dimension reduction and 3 methods of dimension reduction. We want to reduce the dimensions so we can use just the features that best predictive classifiers and get rid of the ones that may cause confusion that aren't helping with our prediction. And that will give us a reduced feature vector. And then in the classification, we're going to use 3 methods and propose with the data set we have now a 5-fold cross-validation for the training and the testing of our classifiers. And from the classifiers, we will get receiver operating characteristic curve, ROC curve. And from that, we will judge a metric on how well we're performing. And what we're going to be doing, I'm going to be doing cross combinations of these methods. So in all total with 3 and 3 and 3, we get 27 different combinations. So we'll be able to analyze 27 different algorithms to find out which is the best. Okay, so texture feature extraction. Again, we're just going to look at the region of interest and extract our texture features into this vector. And the 3 methods we're going to use. We're going to use a grade level co-occurrence matrix. It's a very old method of texture feature extraction and proven and used in a lot of the literature out there. It's based on the spatial relationship of pixels in an image. So next to each other or a distance from each other. And from this, we can calculate second-order statistics of the image texture. This will be 14 Herlich images that Robert Herlich came up with in, I think, 1973 ways of describing these from a co-occurrence matrix. The second will be a local binary pattern. So this is very computational efficient, simple and efficient in describing the local texture feature of an image by calculating a neighborhood pattern, so a neighborhood around the pixel, so we can get local features. And then we can bin these into a histogram and see the overall image, how many of one feature does it, or pattern does it have, and calculate, anything in the histogram, so distributions that we can see. And the third is a multidimensional fractal analysis. So this is basically a combination of wavelet image decomposition and fractal dimension calculation, and it analyzes both the small and the large image. And so what it is you can imagine a tree structure. A lot of people use one wavelet at one frequency, and that may not capture what the best parts of the image. So this uses 4 frequencies of wavelet to decompose the image. Then we run fractal dimensions, calculations on those, and detect which of the 4 is the best. We can apply the same 4 wavelets to that particular decomposition, run fractal dimension again, so we build in a tree structure until we get down to where we're not getting any difference, a threshold, and then we stop there. And the way the fractal dimensions cut it down is we look at the image as a whole and then in pieces as we go down. Okay, so texture feature extraction of the descriptors. And somebody asked me, they said, okay, is this texture in the standard concept of a texture that you would feel, or is this some computer thing that you guys would come up with, technical term? I said, no, it's the same thing, right? And I said, a very good description of a texture is, a texture describes the surface of a feature, and the descriptors say what that surface of the feature looks like. And so these methods are widely used in research of this kind to describe the features. So the first is homogeneity, which is down here. And that's basically the smoothness or the flatness of an image, if you want to put it into a tactile response. Image contrast, which is shown here. And this is basically judging the gray level differences in the image. Do we have very black to very white, or do we have a sub-range of grays? And correlation, and this just looks at the correlation between the pixels. And correlation is good. You can kind of think of correlation as how do they correlate. It's good at looking at repetitive patterns in an image. Then the local feature extraction histogram statistics. And that's good for here, where we can kind of see, we've got a lot of local features that are the same in this image. So that we can go down and we can describe these local features. And then the fractal dimensions. And that's good at both local and global texture features as well as the roughness measure. Okay, dimensionality reduction. And as I mentioned, we want to do this because we want to weed out the features that are not very good at predicting our classes and get down to a small subset that are best predicting our classes. That makes it a lot easier to understand and less computationally expensive. And the first thing is, hit the button, is ElasticNet. And this is basically a regularized regression that captures the L1 penalties of lasso and the L2 penalties of ridge regression. Lasso regression tends to break down if your descriptor features are much larger than the number of data points you have. So here we have 81 patients worth of data points. We may have a lot more descriptors than that. And so this method was developed by Trevor Haskey and colleagues down in Stanford. So if you've ever taken Shannon's statistical class, that's the book. They came up with this with the intent of getting over the problems of the lasso regression. The next is autoencoder, and I'm going to try to paint a picture with a few words here. Essentially, it's a neural network that employs an equal size input and output layers and reduced size interlayers. So the concept here is they're equal size input and output. You put your entire feature vector on the input, entire feature vector on the output, and train the net such that the interlayer is an encoded version and representation of what the overall feature vector would be. And so the smallest interlayer represents your reduced feature set. So you can think of it, if you take this image and mirror it back, you have your input texture features here, and your reduced smallest feature set there, which this encodes that, and then it, in the learning process, decodes it back to match what the original texture feature vector is. And then the third is minimum redundancy, maximum relevance. This is used in a lot of the previous work that we've seen. And it pretty much does exactly what you think it, what the title says. And so this determines the feature subset with highest correlation or predictability to the class. At the same time, determines which features are correlated highest amongst themselves. And so this will, if you have 10 features that all predict very well, we don't need all 10. And so we will reduce something there. Okay, and classification. So the first is support vector machining. And this is used in a lot of literature as well with very good results. So this is a supervised machine learning method to find a hyperplane maximum separation between the classes, between our two classes. And what this kind of brings is that in addition to using a linear kernel, we can use nonlinear kernels. And a lot of the papers have noticed that the classes are nonlinear separable, so a polynomial kernel or a radial basis kernel will be a better method of classification. And then random forest. So this is a supervised ensemble learning algorithm that builds multiple decision trees. And classification is based on a majority vote from the decision trees. So that means it uses a bagging method, which is a bootstrap aggregation, to both build the trees and take the majority vote. And the bagging method is good. It's good with high variance, low bias predictors like classification trees or like decision trees. It's also good in the fact that it tends to be resistant to overfitting your model in the presence of noisy data. And this data may be noisy, so the random forest may come in handy here. And then logistic regression, which is using the linear combinations of the variables to predict the probability of k classes. In this case, we have 2 classes. This is tied right in with the elastic net. And it's in the same software package, and so these two kind of go hand in hand. Okay, and the results analysis. So basically, as we mentioned, with these ROC curves from the classifier. So there's kind of a toy example of 3 classifiers on the colors. And we will basically take the area under these curves as our metric. I point out the dotted line, which is referred to as the coin flip line. If your classifiers fall before that, you might as well just flip a coin as to 50-50 which it is. So you really want your classifiers, these curves, to be up in a direction like this, or maximum area under the curve, and thus we have maximum classification. Also, we want to add into here, for all of our models, combinations of models that we look at and get the ROC curves from, we also want to look at and identify the top performing, or the top features that attributed to that model score. Now, in some cases, we can track this back to the actual features that were extracted themselves. In the case of MR or Lyme or something like that. Now, the autoencoder, that encodes the features, so there's no real way to decode them back. So we would hope to, and I've seen several I've seen several papers that have gone through and actually said, well, okay, here's all the models that we've tested. Here's their metrics of goodness, the area under the curve, and then here's maybe the top 5, top 10 features that contributed to that model score. So we'd like to look at that as well. And challenges and limitations. So obviously we have a small sample size, and that's going to be a problem in training some of our classifiers, especially on the autoencoder, since it is a neural network. Neural networks want as many training data points as they can get, and so that may be a problem with our autoencoder. And 2, we have an unbalanced data set between malignant and benign patient samples. And that somewhat comes with the territory, because obviously if we're looking at a radiologist pointing out regions of interest of biopsy, they're trying their best to not over biopsy. So they're trying their best to say, yes, these are malignant, go biopsy. And the fact that they get benign means that they saw something that, okay, maybe looked malignant, but it was still benign, so that was over biopsy. Didn't need to be biopsy. So we tend to get unbalanced data sets. And much of the literature has unbalanced data sets in it, and they do their, some of them have taken the data set and just thrown out malignant samples to balance out. But then they get data sets where we have 81 patients. They get data sets of in the high teens, low 20s, which is not very many data points. And so there is an issue there. As far as the small data set, as I mentioned, we're hoping to get more data in and boost the size of that data set. And then ideally, we'd like 3D images. Here we're just looking at pixel relationships on 2D plane. Whereas on a 3D plane, now we can look in the Y direction and get more data. And that allows us to even add in some first order statistics such as the shape and the size of the region of interest that we're looking at. And if you read the literature, there's some say that 2D and 3D don't make a difference, and some say that 3D is better than 2D, and it depends on what study you're doing. In the feature extraction and classification realm, most papers for prostate cancer, and I've even seen a lung cancer paper and a brain tumor paper, say that 3D are better. And these are the papers that have compared them side by side with the same methods and come up with 3D is better. It'd be nice to have those, and then we could do a 2D, 3D. And then here's just a project timeline that I've broken down into 3 sections. This is kind of the post-data method analysis, which here we are today. And then we'll fall. And then the concept here is to get all the software in place and test it. So all the modules of software ready and tested. And then the section on the actual data method analysis and the results evaluation. So hoping to get the features extracted by the first week of September. An initial pipeline tested and running. So let's just choose probably all of the features, one dimension reduction, and then one classifier just to make sure we can go through all the way through the pipeline. And then follow up with all the combinations by the end of October. So that's all the cross combinations, sure maybe 27 at this point. And then give time for the results analysis and additional methods. So if we find a classification method, for example, that is not doing well at all, we have time to substitute another one in and then rerun the data on that. And it also gives us time for any additional data that comes in, any new data. And then the post-analysis, which is basically the write-up, and then the official defense in February. And that's all. Yes?
Can you go put your timeline back up?
Yeah.
Yeah, so I would just suggest to you that you're going to need time to write. And I'm assuming you're going to be writing some of the methods in the intro prior, which is got a pretty short time period between any of your analyses and your thesis defense. So there's a way to structure structure your timeline a little differently so that you have time. I'm just a little worried that you won't have time to really absorb your results and interpret them and really discuss them. So just
that's definitely. I mean, as I'm defending in the winter, I mean, I could shove that into like March as long as it gets done in the winter and give myself more time to write and analyze the data. And the way I write, I may need that much more time. Okay.
When you say the software is basically tested, what do you mean exactly? I'm not sure I follow what you mean by that. So do you mean having are you doing fixed or aligned with this?
Yes, for example, some of these are packages that I can download and use. Some I have to write myself. So in the fractal analysis, I've gotten software that will do various wavelets, and so I can use that for wavelet decomposition, and I could run that against tests and say, okay, am I getting this done? Which I have done that. I'm using Gabor wavelets on it initially. And then I've written the software to do the fractal dimension calculations, which is a box counting method. And I've written that, and I already have it verified. So it's just doing things like that, grabbing in. I've got elastic depth. I haven't tested it out yet, but that's one thing I want to do is go through and run test samples through that, just to make sure it's working before I start tying them all together.
Are you looking at MRI images or just tests or PNGs or
The
something?
PNGs from the MRI images.
Okay.
Which some packages do well with PNG images, some do well with only JPEG images, so there's some.
The concern I have, this is probably beyond the scope of the project, to be honest. I don't think it matters much for what you do because you're using an ROI-based approach, and the ROIs were constructed separately in the two data sets, which is actually probably better for this. But just looking at those images, it's very clear to me that there is a distortion in terms of the nature of the data acquisition between your diffusion weighted and the T2s. They don't align with each other. That's correctable if you have 3D images. But so I don't think it's addressable, frankly. But it might be a limitation that might be reasonable to address as well as this for using features. So you can't map like one data set on the other and do something interesting, like divide by the two to be able to spot and have the okay, that is wrong, that is not afterwards, for example, which might aid segmentation.
Yeah, so this is one other limitation I'll bring up now is we may run into problems because we have, as we've gone through, let's say you have a patient and you get 6 slices. Obviously you're going to get a very large slice with a lot of texture information, but some of the smaller slices you get are going to have poor texture information, a lot of texture information. Those may add noise to the data set because even though this is malignant, it's hard to differentiate it from the benign, and so we may have to toss some of those small ones out. I'm not going to at first because I don't want to make assumptions on the data, but that may be something to try and see if I can boost classification accuracy.
It might be interesting to see if the ones that you struggle with in terms of classification are those ones that are kind of like, oh, we have 5 or 6 slices because this is the unusual shape.
Exactly.
Surprised if that's the case.
Yeah, so that's one thing I was keeping in mind when I was looking at the images. Some of these are pretty small, and how much pixel information am I going to get out of that? Are they too small to tell me anything? And then they dirty the waters. Okay.
One question. So are you going to document your testing in your write-up? Your software testing?
Yes. I have a section on the software that I'm using and then they're saying the testing. Okay. Okay. Yeah, I'll try to go through. I mean, I have the images. The 3 images I showed on that other slide were purposely built to be at different ranges of textures where some were homogeneous, some were not, some were local features to go through, and just make sure that I'm getting significant differences as I run through. And then some packages come with test images, so I can actually compare that I installed everything correctly, use their test images, get the same results that they have. But yeah, that's a good point. Okay.
Is a single person drawing the ROIs, or is it multiple people drawing the ROIs?
As far as I know, single person was drawing all the ROIs. I don't know the gentleman's name, but, I said, well, yeah, he works with Dr. Fergus Coakley, who's the benefactor of all of our data here.
Multiple people could have that's
True. Yeah, and that kind of gets into the, okay, multiple people with different experience levels. There was a study I read in 2017 from Stanford that came up with a computer model. And their computer model did better prediction than a radiologist with 2 years of experience, but it performed worse than a radiologist with 15 years of experience. So yes, that would have batch effects, yeah. But this is just the one person so far. I'm assuming that will be the case in all the new data that we're getting.
So how will you have one radiologist controlling that? There's always value to have multiple, so you can characterize the intraoperative variability and human performance levels.
And definitely, and ultimately, in order to build a more generalizable model, you do need to maybe run the calculator. The ideal thing to do, though, would be to ultimately have a way to draw it out by yourself, obviously. So that way you can get away from data models.
And that's, oh, you can go.
Right. So that is beyond the scope of analysis. It's actually, as we speak, a feature study session on that constitution. I will probably share information talk. So that calls for almost 60 elements.
Yeah, Arshan is doing that and doing a lot of the image, upfront image work that I'm being the benefactor of. She was our TA in machine learning.
Exactly, it's absolutely well beyond the scope of this project. But it makes your project a lot easier to have one.
Yeah, they won't give me enough credits, so I have to stop here. Excellent. Thank you all for coming and trekking up into the, especially Guillaume, where I've come a far distance. Okay.
Oh,
Do you have papers to sign?
Yes, I have the paper.
So you have, everything, then the next year.
Actually, I have 2 copies of the paper.
but, good stuff. Do you want me to close the door?